Okay, this will be based on the handout that you had already. And then we're going to go back to the Desmos. So the handout I had you open up is this one. So there's really interesting writing on here. For me, it makes a lot of sense. For you, it may not make as much sense, but you'll notice it's also about the derivatives of inverse functions. And this example right here talks about one approach that you can use to find the derivative of inverse functions. The reason why we don't learn this approach exclusively is because this has a really strong limitation. So in example 1, f of x is x squared. And we can figure out using our normal method that f inverse of x is going to be the square root of x, right? If you switch x and y, take square root of both sides, you get the positive and negative square root of x. We're just going to stick to the positive square root of x, okay? That's pictured over here. So this is on your page 2. And it's similar to what we did. So we have the function, the derivative, the inverse, the derivative, check, check, right? Okay, so if we're looking at f prime of 2, what you would expect is to look at the inverse at 2, but you don't. That's because we're talking about the inverse point. So in the function f, 2 is 4. And in the function f inverse, that switches. So you got to be really careful with that. That's a very easy way to get mixed up when you're trying to do inverse function derivatives. So this example 1, otherwise, besides the same things, I think is a really good example of one of the 3 ways you can do an inverse function derivative. And this one hardly ever works. But I'm mentioning it because it does work sometimes. Sometimes it works out where you have a formula for f that you can actually solve for f inverse. And once you do that, you still have the same things though. We talked about how the slopes are reciprocals, 4 and 1/4, but they're at the inverse point in f at 2 and in f inverse at 4. But sometimes you can actually solve. There's a second option you can pursue. The second option you can pursue is based on implicit differentiation. Okay, so if you look right here at this box, there's a really interesting formula I'd like to point out. And that's this one. I know it's hard to see on here, but it should be legible on the handout. It says dy dx at the point AB equals 1 divided by that should be dy dx at the point BA. And what it's saying is we have reciprocal values, right? If you have dy dx here and you take the 1 over dy dx, that's talking about the reciprocal. And it's at inverse points, just like we talked about in Desmos, just like we talked about on here. AB, the inverse point is BA. So this is the second thing that you can do. So you can, like it spells out here, find the inverse by switching x and y, take the derivative and substitute in. So what does that look like? Well, if we're looking here at y equals f of x equals the square root of 5, what we're talking about doing is saying x equals y plus 5, the square root of y plus 5, excuse me, and differentiating right here. So if we differentiate with respect to x right here, on the left side, the derivative with respect to x of x is 1. On the right side, I need the chain rule. So I have an outside function of x to the 1/2, or y plus 5 to the 1/2. The derivative of the 1/2 power function is this. And then I multiply by the derivative of y plus 5. The derivative of y with respect to x, I write that as dy dx. The derivative with respect to x of 5 is 0. So this right here can be used to do exactly what we want. We can take this equation and this dy dx is a slope calculation. So it's not actually the slope because it's in terms of y, but we can use it to calculate the slope. And that's because, remember, when you're working with the inverse, when you do an inverse point, the input of the inverse is the y value for the original function. So that's why this makes sense here. A little bit of algebra. F inverse of 3 means 3 is, multiple choice, is it the x, the input, or the y, the output for f of x? So think about it. So that's saying f inverse of 3. We don't know what f inverse of 3 equals. But what does it mean? 3, if I'm in the original function f of x. Is it the input for f of x, or is it the output for f of x? That's what we're trying to figure out. It's the y value, okay? If you draw it out in a table, the 3 is occupying the same spot right here as this 4. That's all I want to take time to do on that one. Let's check out example 3. How about the derivative to the inverse of y equals x cubed plus x at 10? We have the graph of x cubed plus x and the inverse of x cubed plus x. We want the slope of the line tangent to the inverse at x equals 10. However, we can't actually solve for the inverse directly. So what are we going to do? Well, we can do what is suggested, which is use implicit differentiation. So how's that going to work? They've been helpful and spelled that out for us already. x equals y cubed plus y. Good practice for later. What's the derivative with respect to x here? All right, differentiating with respect to x. We get 1, we get a 3y squared dy dx plus a dy dx. Factor dy dx out, divide both sides by 3y squared plus 1. And we get that. Yep. Now, the problem is, what value do I use? Because it says 10. But we don't just want to jump right in with knowing that x is 10. Because when we look at this, we probably wonder, which x is that for? Kind of hard to figure out here. And it requires just a little bit of parsing. So we wish to find the derivative at x equals 10. So what's it the derivative of? It's the derivative of f inverse. So if we look at f, it's an output. So the question is, how do we get this? Because that's what I need for here, right? That says a y value. Yeah, so how do I get that? Now that you're done thinking about it, we have a y value and we want an x value, right? That's what we got. Okay. That means we can solve this. This would be, give me the x value when the y value is 10. So there's a few different ways you can solve this. It's a minus 10. So that's the equation we want to solve. So we could graph that and look for the zeros. We could graph this intersection and look for the points of intersection. That's also fine. We also got a pretty helpful graph over here, right? Pretty helpful graph. So the graph might work. Anyway, I'll let you figure out how you're going to solve that, and then we will meet back here in like a minute. You got 2, yeah? 2, okay. We can actually check 2. 2 cubed is 8, plus 2 is 10, minus 10 is 0. The remainder, or f of 2, is 0, so we know that works. So this is 2, and this is 2, which means, to get our answer here, we want to do a dy dx when we're at the point 10, 2. So we use our y value of 2. So that's 3 times 4 is 12 plus 1. That's 1/13. Okay. And f prime is 3x squared plus 1, yeah? 3x squared plus 1. Did I do f prime right? Pretty sure. X cubed plus x is 3x squared plus 1. It's so weird to shift back out of implicit differentiation, isn't it? But you got to be able to. Okay? So f prime of which value? 2. What does it need to be? What was the thing we know already? We know that these ought to be reciprocals. So is f prime of 2 the reciprocal of 1/13? It is, it's 13. Okay. And this right here is the third way. And that's what we spent most of our time developing on Desmos and before the break. Reciprocal slope at the inverse point. So last time I'll repeat this today. If we're at 10 in F inverse, we want to be at the X value that corresponds to 10 in F. So F inverse prime at 10, F prime at 2 are reciprocals. F prime of 2 is 13, so that tells me, even without doing all of this, that F inverse prime of 10 is going to have to be 1/13.